Okay, being
Okay.
recorded. Got it.
Okay, go ahead. Thank you.
Got it. Yeah,
Yeah.
All right. Are we still sharing the screen yet?
I think so.
Okay. There's usually green box. Okay. All right. It's a pleasure to welcome David Tsang from the University of Bath for today's pizza seminar. Dave did his PhD at Cornell and then a few postdocs in North America before he moved to the UK. And Dave is going to tell us today about probing nuclear physics with Newton-style mergers.
Great. Thanks, Vanessa. It's a great pleasure to be here at the center of many neutron star things and nuclear physics people. I'm going to be talking about the work I've been doing over really the last decade, starting with a paper I did with Roxandra way back in 2000. Well, we wrote it in 2011, 2012 was published when we were baby postdocs. All the way up to really a lot of the stuff I'm going to talk about today is the thesis work of my previous grad student, now postdoc, Duncan Neal, as well as the master's student, Becky Preston, who was a master's student with Will Newton at Texas A&M Commerce. She is now a graduate student, a PhD student at Southern Methodist University. So I expect great things from her coming out because she was an amazing master's student. So I'm going to be telling you about basically how we can probe nuclear physics with neutron star mergers. And, you know, more than just saying, oh, something titled deformability, something APR, something SLI4. We're actually going to try to figure out what some of the physical parameters are that nuclear physicists want to know. So we can start with the basics. Why are neutron stars important to nuclear physicists? We're then going to move on to thinking about which regions of a neutron star tell us about which physics. Because really it's what type of physics we care about that determines which regions of the neutron star we should be looking at. We're going to look through the multi-messenger observables that we can use to probe these different regions. And I'm going to focus in on this work I've been doing over the last decade called Resonant Shattering Flares, looking at this particular phenomena. And we're going to compare, we're going to see how we can constrain nuclear physics with resonant shattering flares and compare them to the outputs of collider experiments. Okay, so why are neutron stars important to nuclear physicists? Well, I'm sure you've all seen this diagram. Anybody who works on neutron stars or nuclear physics has seen this diagram on every other talk. We have the phase diagram of nuclear matter. We have temperature going this way in MeV, and then we've got net baryon density. Nuclei sit around here. This is the saturation density. And colliders, terrestrial collider experiments, can sort of probe slightly higher density, but they really get really high temperature. And you know, you show this to a nuclear physicist, and they say, "Oh, well, neutron stars are great because they probe us around here at this low temperature, high density region, particularly in the cores." Here, by low temperature, I mean low compared to the Fermi temperature, because of course neutron stars are degenerate. So a key point here is what's called the saturation density. This is the density of most symmetric nuclei, or what of most nuclei, basically, where in particular the nuclei that are equal numbers of protons and neutrons. If we look at the cold infinite nuclear matter equation of state, so this is energy versus baryon density, and this is just a cartoon. We don't actually know this that well. We know this part fairly well, but we don't know the other parts. I'll show in a second. So this is the, there's a minimum where we have what's called the saturation density. And when you have an energy versus a density, right, the slope is going to be a pressure. And if you have a negative slope, you have a negative pressure. Things don't like to be at negative pressure. That's why things, if you just took an infinite field of equal number of protons and neutrons, they would condense, if they were sort of in this region, down to clusters or nuclei or nucleuses. Right, so this is for symmetric nuclear matter, equal number of protons and neutrons. If instead you swapped out all the protons for neutrons, you would get some other equation of state. It's a little bit higher than the one for symmetric nuclear matter. And the difference between these two is what we call the nuclear symmetry energy, the cost of exchanging neutrons for protons, or protons for, yeah, cost of exchanging protons for neutrons. And you characterize this by sort of eSym as a function of n. And we do like what any physicist does. Whenever we have something we don't have fully characterized, we Taylor expand. So we characterize this by a parameter J, which is the value of the nuclear symmetry energy at saturation, the slope at saturation, and the curvature at saturation. Okay, there's a little bit more to do here than just this, but more or less that's the important bit. Okay, and it's these are going to be the parameters. These are the main parameters we're going to be looking at today. Now, neutron stars are stars that are full of neutrons, right? They have very high asymmetries in neutrons versus protons. So really, this phase diagram should be extended to 3D, looking at what's called isospin asymmetry, number of neutrons versus number of protons. And really, compact stars sit out in this region over here at low temperature, high densities, but also high isospin asymmetry. So really, this is the diagram you should be looking at. So symmetry energy is important, particularly for heavy ion collisions. People run these big collider experiments to try to measure this quantity. In particular, these J and L, the value of the symmetry energy and the slope of the symmetry energy. These are important for determining the structure of heavy ions, and you have a lot of different ways of getting at this that are sort of a little bit above my head. So, but we have nuclear masses, there's giant dipole resonances, dipole polarizability, heavy ion collisions in general, and then neutron skin thickness. Now, neutron skin thickness, if you have a heavy element, lead, there's generally more neutrons than protons in it. And because of that, the neutrons stick out a little bit. And that extra thickness is called the neutron skin. That's what's measured in these neutron skin experiments, also what's measured in PREX and CREX, which is down here somewhere. PREX has way big error bars, which you can't really see on the projector, but it's like this big error box here. It's a little bit weird that it's so sort of high and people are still trying to figure that out. But we can ask, there's so much effort gone on in trying to find, to sort of narrow down these parameters. Can we use astrophysics to help with this? Is there an astrophysical measurement that we can use to constrain the symmetry energy? Well, to get at this, first we have to think about which regions of a neutron star would tell us about the symmetry energy. Now, neutron stars are the best stars because they are so interesting. They have so many different parts to them. We have an ocean, we have a crust. The outer crust is a Coulomb crystal with an electron gas. The inner crust, you pass neutron drip, you start getting a neutron gas with that Coulomb crystal. There's a very interesting region that is a nuclear pasta that may or may not be a significant fraction of the mass of the crust. Then we move on to the core, where you have free-floating neutrons and protons, a neutron superfluid, a proton superconductor. And then deep in the core, we don't know what happens. And I really want to emphasize this. We do not know what happens in a neutron star core. If you ask an astrophysicist, we generally say, oh, it's neutrons and protons, because we know how to calculate things from neutrons and protons. But if you ask a nuclear physicist, almost all of them say, no, it's probably something weird. We have no idea if this is going to be neutrons and protons or not. It could be something like a quark gluon plasma, where the quarks just become deconfined. It could be something like hyperons. There could be extra degrees of freedom that sort of pop in, like pion condensates, kaons. There's all sorts of different ideas for what can be going on in this region. And the reason that we don't know is precisely why neutron stars are interesting. They are beyond the parameter space that we can currently probe with nuclear experiments. So we have no idea what is going on in here, okay? The core, so this is actually what makes cores so interesting, is that if we can get information about the cores, it might tell us about this state of matter, which we're not really sure what it's made of. But for the purposes of studying symmetry energy, which is a nucleonic parameter, you don't really want to be using the core because we have no idea if that is actually nucleonic or not. If it is, great, but we don't know. So with that in mind, the way we approach this problem is we took an extended SCRM EDF developed by Will Newton and his master students. Will takes this extended SCRM energy density functional, and then that extension allows him to basically put things in terms of the symmetry energy, reparameterize things in terms of the symmetry energy parameters. And then to capture our ignorance of the inner core, after a certain point, we just attach it to two piecewise polytropes. And those piecewise polytropes, you shouldn't take them seriously at all. They're just there so that we have parameters that can sort of capture core dependence, right? We're not saying at all that that's what that's realistic. A realistic core may have like a first order phase transition or something, which we wouldn't be able to capture with this. But this allows us to capture sort of the dependence on the symmetry energies in the region where we're sure things are still actually nucleonic. So we can ask, okay, what multi-messenger observables probe these particular regions, right? These sort of the crust to the outer core. That's where things stay nucleonic. Okay, what observables do we have that actually probe those regions? Well, the main electromagnetic observables that we have from neutron star mergers are, of course, kilonovae and short gamma ray bursts. These are both fantastic. Kilonovae in particular, to understand them, we have to understand the production of all these heavy isotopes from the R process. So like things like EFRIB feed a lot into sort of producing what's going on with kilonova. Short gamma ray bursts are super interesting. We still don't understand the basic mechanisms behind what's powering these jets. But for the nuclear physicists in the room, I should say, short gamma ray bursts, the neutron stars collide. They form either a black hole or a hypermassive neutron star with an accretion disk around it. That accretion goes onto the central compact object, and you get a jet. Somehow, magic jazz hands happens, and you get a jet. And if that jet's pointed at us, we see a short gamma ray burst. Okay. A kilonova happens when you merge these neutron stars and it flings out all this material. And this material is very neutron rich, but suddenly you decompress it. And then all the neutrons that don't want to be by themselves, they run into the nuclei and make heavy nuclei. Those beta decay, and you get radioactive signature of a kilonova. Oops, that's my flashlight. Radioactive signature of a kilonova. Okay, both these things are fantastic, but they tell us a lot, mostly about the messy post-merger physics, right? All the messy gastrophysics. There's so many degrees of freedom that you have after you smash these things together that it's really, really hard to extract information out about the progenitors. Okay. Anything you can say about the progenitors are sort of after some suite of numerics that, maybe you can predict the masses that went in, but I really don't believe that that's the case. The gravitational wave signal might give you something a little bit more, because the gravitational wave signal, of course, primarily, at least currently, gives you information before the merger. In particular, the sort of, to lowest order, you get the chirp mass. To the next order, interesting thing is the tidal deformability, how squishy the neutron star is to tidal deformations. For 1708-17, there was some upper bounds and sort of a kind of measurement that includes zero of the tidal deformability of the neutron stars involved in 1708-17. It didn't tell us anything that we didn't already know about neutron star equation of state, but it showed that we can maybe expect measurements of these in the future. Additionally, you might say, okay, there's also neutron star radii. Of course, there's the NICER experiment on the International Space Station, fantastic mission that looks at X-ray pulsations from rotating neutron stars. Looks at hotspots basically, and by modeling the space-time ray tracing, you can sort of infer what the radii of these neutron stars are. You have to stare at them for a long time. There's sort of certain model dependencies. Atmospheres are tricky, but you get down to error bars that are a few percent, like 5-10%. Okay, and probably with these will probably get down further to like a few percent. These are hard measurements to do. They take a lot of time. The next generation needs just a lot more collecting area to sort of get a lot of these things. And it'd be fantastic if we had this full mass radius relationship all the way for like all the different masses of neutron stars. But that would take quite a lot. We'd have to basically populate all these curves with measurements, and we'd have to do a lot better than sort of error bars that look like this. However, with these sort of few mass radius measurements, the sort of lowest upper bound, the maximum mass, the tidal deformability, and F mode. F mode, if you the fundamental mode of a neutron star is basically the same physics as the tidal deformability. So all these properties are basically functions of the core. They basically depend mostly on things close to the core of the neutron star, somewhere around a few saturation. And so they're really probing regions where we don't know if the physics is nucleonic or not, right? And one has to be very careful when trying to infer nucleonic properties from such measurements. So to sort of illustrate this, we can do a Bayesian inference using the NICER data and the 170817 tidal deformability. Here, we've taken our nuclear physics with viable sort of neutron stars, things that are sort of stable. That's our gray, that's our priors. And then our red are our posterior. So the way you want to rate this really is, where is the red different from the gray, right? That tells you where is there extra information about that these data give you, right? And you basically see that for L and J, there's not really any difference. You're not really gaining any extra information. Where the extra information is in the core. And maybe a little bit of K too, because the K is sort of the outer inner core. So what this tells you is that these, like, in this sort of rough way, these data really only inform what's going on in the core. Maybe not the central core, but like, sometimes at a few times saturation density. Okay, so it contains almost no information about the crust and the outer core. Okay, you can sort of do these kinds of analyses, and for different heavy ion collision experiments, as well as other mass radius things, and you get this sort of dependence. This is a very nice paper by Betty Tsang and her group, no relation. Betty is a very famous experimental nuclear physicist. And basically you see that, so this is just a cartoon of what the equation of state would be and where the different constraints sort of sit in the densities as a function of density. And most of the tidal deformability and radius measurements really probe in this region above 2 saturation. That's what we want. That's the point. Whereas most of the heavy ion stuff is sort of out here. There's maybe a little bit over here as well. This is just another way of showing the same thing for non-parametric equations of state. So another way of probing things is to look at the spectroscopy of the system, right? If you imagine these neutron stars as giant nuclei, giant atoms, then you might say, okay, I studied the spectrum of it, and that would tell me about it. In this case, so this is a very nice paper from Luciano looking at the gravitational wave spectroscopy of a hypermassive remnant. So here, in this situation, you imagine you merge two fairly light neutron stars together. They leave a remnant neutron star that's hypermassive, and it's sort of oscillating, it's ringing down, and maybe you can see these oscillations. This isn't really visible with current generation of gravitational wave detectors, but will probably this magnitude of things, which should be visible with ET or Cosmic Explorer. I just want to highlight something here that I am very guilty of as well. But notice, when we say we study the nuclear physics, we astrophysicists, we just tend to throw on 4 equations of state and call it a day, right? We just say, well, we just throw a soft equation of state, a hard equation of state, a medium equation of state, and and then one for fun. And we say, well, you nuclear physicists figure it out. And that's just not a good way of actually communicating with people. One of the things that I've been really sort of trending towards lately is moving away from talking about single equations of state. It's not really a criticism of these guys, because you cannot run Bayesian inferences when you're doing numerical relativity simulations, right? There's no way you can run 1 million GRMHD simulations and hope to ever, graduate students. It's not really a criticism of them, but it's more a criticism of our approach in general in astrophysics. We need to really talk to the nuclear physicists more and talk their language so we produce things that are useful to them. And I'll talk at the end. I'll do some advertisements about some of the efforts that that I'm leading to sort of push us in this direction. Okay, so this spectroscopy is really interesting. This idea of spectroscopy is really interesting. This looking at the asteroseismology of these neutron stars, that can tell us a lot of information. Like I said earlier, the F mode doesn't actually tell you that much about the outer parts of the star. It really tells you more about the inner parts of the star. Okay, but we can look at other modes. If we can see other modes, then we can probe different regions depending on where those modes sit. So we want an observable that can be used to probe the structure of the inner crust and the outer core, and therefore the nuclear symmetry energy. And so the question, Alex, is what are resonant shattering flares? And there's my little animation. During a COVID Christmas, it took me the entire COVID Christmas to program that animation. So we'll watch it again because it took me all Christmas. So the neutron stars are rattling around, and then before they merge, something happens. A flash happens. Okay. Now, what originally motivated this work was Ruxandra came to visit me at Caltech, and she said, let's figure something out. And we looked around and we said, well, there are these SGRB precursors that we don't understand. So these are little blips that happen before short gamma ray bursts. And, if you assume that the merger happens fairly close to the short gamma ray burst, like within several hundred milliseconds, then these should be occurring before the merger. And we tried to figure out what those were. And we came up with this model, which is resonant shattering flares. So the orbital energy, because the orbit is emitting gravitational waves, the frequency sweeps up faster and faster. And if you have a mode that can couple to the tidal field, you're naturally going to sweep through all these frequencies up to several kilohertz when the stars touch. And so if you have a mode that's resonant within that frequency range, you can excite it. If that mode strains the crust fast enough, and remember this is a solid crust, like all solid materials, there's a breaking strain. You can sort of bend it past a certain point. It's ridiculously strong in a neutron star, but you can bend it past that point. It'll fracture, and you'll convert that energy, some of that energy, into seismic energy. You do that over and over and over again. Eventually, the entire crust is at this elastic limit. It scatters all the energy, scattering all the energy to high frequencies, which can then couple to a strong magnetic field. That when those strong perturbations of the magnetic field go nonlinear fairly quickly, spark several pair of photon fireballs. Those blow out, and those colliding shells give you gamma rays. Okay, so it's a long involved process there, but We've done the physics in each part of this to try to basically work out, okay, what's going on, what could be causing these gamma rays. So the most interesting part for us in terms of understanding the nuclear physics is which mode are we talking about? And we looked around, and the only mode that has around the right frequency range to occur before the merger, strange the crust enough, and can give us these resonant shattering flares is the L equal to 2 crust core interface mode. Okay, the F mode would be enough, but it's too high frequency. It doesn't really reach that. G modes couple well, but they don't strain the crust. Crustal modes work, but they're the wrong parity to couple to the tidal field. So the I mode, the interface mode. So this mode exists because there's a transition from a solid crust to a fluid core. Whenever you have these kinds of transitions in systems, they tend to lead to eigenmodes. It's just a a fact of ODEs. We think what's happening is at that point where it was a flash, where was that flash, the interface mode gets excited to the large enough to cause all these shatterings, which blows out in a paraphoton fireball. And we see that as this precursor, this little blip, this precursor blip. This relatively isotropic, especially compared to the short gamma ray burst. And if we get a multi-messenger detection, if you can have a detection from LIGO where you can just read that frequency off at that particular time, that gives you the frequency of this mode. So you can do, so even if you don't see the signature within the gravitational waveform itself, you can still read that frequency off just by the timing. So if you have this consistent timing, it lets you do precision asteroseismology of this particular mode with a true multi-messenger detection, which is really, really cool. Yes.
It's very interesting what you're saying. You're always focusing on the equation of state that gives you the frequency of the mode, but you didn't say anything about the damping of the mode.
Yes, so the damping.
And this connects with the work that Luis is doing.
Yes, so it's the driving is so hard in this that I don't think damping matters too much, but it is something you want to worry about sort of at the next order. We don't include damping currently in our calculations, but it is something probably later on we want to include. Right now, there's.
When you say next order, what do you mean?
I just mean that it's probably a small correction. Probably.
You don't know the value of damping.
Yeah, we have no idea how to calculate it. So, we could put in some guess, but you can look at sort of corrections different orders. I think the most important correction we still need to do, which I might come to later, but is probably the correction for the nuclear pasta region. So we currently don't include that nuclear pasta region, for instance, and that's probably going to affect the frequencies more than including the damping terms would.
Saying this because Luis is actually computing transfer that may allow to keep these damping times.
Yeah. So the driving is so hard here that as long as the resonance is vaguely sharp, it should be fine. So I don't think the damping should be strong enough to stop that resonance from getting all the way up, but it does shift frequencies, right? So you do have to worry about it eventually if you want to be accurate. So yes, it is an important thing that we haven't considered yet. That I would love to consider, but it's very difficult to calculate the damping in these things, as I'm sure you know. Okay, right. So I've told you what these resonant shattering flares are. Question is, how can we use these to constrain the nuclear physics? And how does that constraint compare to collider experiments? So universal relations are all the rage these days in neutron stars. And as far as I can tell, universal relations just means an integral mostly gives you the same answer when you integrate over all the details. So in that spirit, we have a universal relation between the density weighted shear speed and the I mode frequency. So this is for all our equations of state or at least a subset, so that we're not completely blacking out this thing. We have this dependence on the density weighted shear speed, giving the IMO frequency. So really, it's about the shear modulus within the crust, the sort of average shear modulus within the crust, and that's determined by composition. So it's really the crustal composition that matters for us. And so we can take all our equations of state, we can stick them in all our EDFs, we can stick them in a liquid drop model, calculate the compositions, and then calculate the shear moduli that we get out, and then work through and look for what the different modes. So here is another corner plot. I've stuck in an artificial, and I want to emphasize this is not real, because we haven't had a multi-messenger detection yet. But I've just stuck in a 250 hertz posterior. So a 250 hertz signal. And I've taken, and the blue is the posterior here. And again, you want to look at where there's a difference between the red and the blue, the prior and the posterior. And really, you get a strong constraint on this sort of in this JL plane. Okay. And so if you detect one of these things at 250 hertz, you would say, this is my constraint on the symmetry energy. And this is for a single detection. And already it's fairly comparable to a lot of these heavy ion collision measurements, which is a surprise. It was a surprise to me that we could do so well with a single measurement. I'll show multiple measurements in a bit, but if you might ask, well, okay, that's a fake injected frequency. If I inject a different frequency, we have something relatively similar. If we fold in, so I think this is only folding in the nuclear masses. Maybe also the giant dipole resonances. But if you fold in some of the nuclear data with that posterior, you also get basically some shape like this. So you can start really providing a meaningful astrophysical constraint on this nuclear parameter that people spend a lot of time trying to measure. If you have more than one measurement, you can do even better. So this is some preliminary work on an upcoming paper. And here we have pretending we get multiple detections. So the red is for a single detection, and then the blue is for 3 detections. Sort of looking at the sort of optimistic case where we have quite a range of different masses involved. It turns out the frequencies don't really matter. The frequency dependence on the mass is very flat. So you don't really get that much leverage by looking at different masses. But sort of we took the most optimistic case, and you basically get a much narrower, well, not insignificant narrowing of that parameter space just from 3 detections. So we can do better. If you don't include the nuclear data, though, then it's really dominated by systematic errors. So you have to include the nuclear data to get rid of those systematic errors before the statistics start playing a role. Nuclear people often don't like looking just at JNL. They like looking at symmetry energy really as a full function of density. And so here is just a plot. We're just taking our EDFs and we've just looked at, so the orange is the prior, our model priors. And then the green is sort of the ones that are selected by the posterior. This is with no nuclear data involved. And what I want to point out here is that, we're right in this region where we can start to distinguish between sort of models that prefer these sort of higher values that the heavy ion collision people like versus the Cowley-FT people, which prefer slightly lower values. See if I have this. Yes. Indeed, if you include the nuclear data, not necessarily these points, you can see that these one sigma constraints, if we had a 250 hertz detection, could distinguish between the N2LO Cowell effective field theory predictions. The background here, of course, is that right now there's a little bit of tension between what the chiral EFT people predict and what the experimenters are seeing. And they constantly argue back and forth about who's right. Really, they're probably both right. Remember, this is actually a projection down in the 3D plane, right? Because there's also a isospin asymmetry in this axis too. So they're probably like, not too far off. And we'd be closer to, so the chiral EFT is for pure neutron matter. It's a calculation for pure neutron matter. And so we'd be closer to that than to these guys, which are closer to symmetric. So there's probably something like that going on too. But again, this is nuclear physics that's a bit above my pay grade. I'm a simple country astrophysicist. Okay. Right. So we can do pretty well with this if we get a detection. Surprisingly well. I was surprised anyways. Moving on to some astrophysics, can we actually expect to see any of these things? Well, I already told you we were motivated initially by the fact that there are these precursors, right? These precursors do exist for a handful of short gamma ray bursts, like a few dozens. We don't expect to see a ton of them because they have to be fairly close in order for us to be able to see these blips, right? So you just have a selection bias. It has to be nearby objects. But I told you earlier, these flares are probably much more isotropic than the beamed gamma ray bursts, right? So you expect to see a population. If these are really RSFs, then you expect to see a population of orphan resonant shattering flares that aren't accompanied by short gamma ray bursts, just because the short gamma ray bursts are pointed in a different direction. Okay, so I just looked through the literature. The problem with this is that you have this huge bias within the GRB community that if something is short and dim, they're not going to follow it up and find the redshift. They'll either think it's too far away or they'll blame it on magnetar flares, which are just as cool. I don't know why you wouldn't want to look at it, but anyways, so these are the few short gamma ray bursts that are sort of in the right duration, about 1/10 of a second, or a few tenths of a second, and the right fluences. So somewhere between 10 to the 46 all the way up to maybe 10 to the 50 ergs. And so these are sort of candidates for a lot of the ones with the stars here. These are redshifts that aren't identified by afterglow, but rather the bursts error regions have this galaxy sort of nearby. So you have to take that with a little bit of a grain of salt. But probably some fraction of these are indeed cases where they're right and some of them are wrong. But we have this population. So there's a good question here, which I'm having a master's student in Toulouse working with the SPOM team. SPOM is a Chinese-French mission with a gamma ray burst component. They're going to be basically trying to see if there is indeed a local orphan component, a local RSF orphan component within the SGRB population. Basically, is there an extra tail of these very short duration, very dim gamma ray bursts that exist in the population? Few number statistics it looks like that, but it's a few number statistics, and there's all sorts of weird biases that creep in. I'm not sure. It seems promising though. Okay. If we look at possible gravitational wave sources, we know we have neutron stars, we know we have neutron star black holes, and we know we have black holes. Post-merger, if the two neutron stars merge, you can get two different results. You can get a hypermassive neutron star that's left over with some disk and ejecta, or you can get a black hole and a disk and ejecta. Eventually, this will go to this probably, unless these are super light neutron stars. If you have a neutron star black hole, you either get a black hole with ejecta, or just the neutron star gets swallowed whole and you get no tidal disruption. Black hole, I assume, and if there's no matter around, you get no electromagnetic emission. Okay. The possible counterparts. So remember, short gamma ray bursts and kilonova both require you to disrupt the stars involved. They require you to either make an accretion disk, or they require you to spray out all these heavy elements, right? All these heavy nuclei. This works in these two cases, but if that neutron star gets swallowed whole, you do not get a short gamma ray burst or a kilonova. Okay, but you can still hit that resonance because that resonance occurs before the merger. It doesn't need a tidal disruption. So in this case, an RSF might be the only thing you can get. There's some talk about magnetospheric flares, but those tend to be very, very dim, much dimmer than an RSF would be. You can look at the parameter space here. So look at the bottom numbers here. The top numbers are sort of like the most pessimistic case, and the bottom numbers are sort of more realistic. These are results of a big pop synth analysis that we did. Black hole spin on the bottom, sorry, on the top, on the vertical, and black hole mass on the bottom. And you can see for reasonable parameter space, unless these things are spinning super fast, unless the black hole is spinning super fast, you're not going to get a tidal disruption. You only get a tidal disruption for about 1.4% of the population. 98.4% will give you still RSFs, and then a very small fraction won't give you anything. It'll reach the ISCO before the resonant excitation occurs. Okay. Now, it depends on basically how massive are black holes that are with neutron stars. I thought it was very telling that the fiducial LIGO value that was used, Andy, way back when was like 10 solar mass, and then people realized that they wouldn't get kilonova anymore at 10 solar masses unless you had a ridiculously high spin. So all of a sudden, the fiducial mass shifted to 5 for no astrophysical reasons, but because then they could talk about kilonova. But I think basically the vast majority of black hole neutron star mergers will not have tidal disruption events, will not have tidal disruption associated electromagnetic counterparts. There's still caveats about when you can get an RSF because you need a very strong magnetic field. But it could be that the RSFs are the dominant electromagnetic counterpart for these neutron star black hole mergers. So I talked about the main thing that stops you from having these all the time is really the strength of this magnetic field. It turns out the magnetic field strength, the surface magnetic field strength, is the main bottleneck for getting energy out of the star. You need to extract it from the crust in order to spark that fireball. And if the magnetic field isn't strong enough, you can't extract the energy fast enough to be able to make it bright to see. And that's the main bottleneck. So if we look at, this is a very, very simple model that we put together, a very simple fireball shell model that we put together. And you see that, you only get strong emission, like about 10 to the 49. This is assuming like a gamma ray efficiency of, I think, a few percent. You only get about up to 10 to the 49 with 10 to the 14 and a half Gauss surface fields. Now, that sounds really high. That is really high. Magnetars are like 10 to the 15 Gauss, but remember that's dipole. Surface fields could be an order of magnitude or two higher because you're more likely to have a lot more energy in higher order multipoles. Here's just another plot showing the same kind of thing. So how the redshifts are basically how far we can see them with Fermi, with different magnetic field strengths. So we expect the surface field to actually be quite complicated, particularly for high magnetic field things. If there's any crustal evolution, that will sort of tend to push you towards like these holotractor states that have these very complicated magnetic fields and toroidal fields, et cetera, et cetera. However, we know from simulations of these crusts, particularly done in Valencia, and by Jose Ponza's group and related characters, and by Andrew Cumming and McGill and Kostas Gogilatos and Patras, that when you have strong magnetic field threading only the crust, that will basically dissipate within on a time scale of 10 to the 6 years or so. So basically, if you have only magnetic field, if the magnetic flux is basically only supported by the crust, these fields should decay in about 10 to the 6 years. So you can't have these things last very long. Whereas the mergers take about 1 billion years to do for most things. You might get lucky and just kick something so that it merges right away, but you can't count on that. Most of these things are 1 billion years old. The reason that you might think that you only have a crust field is because of the Meissner effect, right? When you form a superconductor, you expel the flux. Okay, but I always cite then a paper by Vanessa and Nils that, well, if you cool fast enough, you actually freeze in that flux before the Meissner effect can sort of completely throw everything out. So if you cool fast enough as your neutron star is forming, you may be able to have a core supported field. In that case, you should last a lot longer than just a crustal one. Okay. Another way of putting this is we need these strong fields to make this an RSF. We can confirm these are RSFs if we get a coincident detection and we see that it occurs before the end of the trip, right? So that it occurs during the orbit. If that's the case, then that means that we know something about the core, the field evolution. Most likely that we have significant core field still. So that's an interesting side tangent. But we do require fairly strong fields. At least the surface fields have to be strong in order for us to see them. Yes.
So is the estimation magnitude of magnetic field inside the core? I mean, the rough estimation.
Oh,
Strength.
I don't know. Vanessa?
I mean, I guess the answer is no one really knows what
Yeah.
the core field looks like.
Yeah, we don't know.
So basically, what you have shown is the surface.
Yeah. It's only so for me, it's only the surface stuff that matters. Okay. Yeah, because that's the energy extraction. The energy doesn't stay very long in the magnetic field. It sort of steepens very quickly and then goes nonlinear, but reconnects. Photon fireball. So, yeah. Okay, so here's a pop synth. Here is an extremely generous, and I want to emphasize, extremely generous assumption that all neutron stars have their magnetic fields forever, which is a terrible assumption, but it provides us with an upper bound on these rates. Okay, and so if we assume that, and we sort of say, okay, well, we only see magnetars for so long, because they sort of move past the death line, or they just the crust part is finished going, so we don't see them pulsate anymore, and they spin down. Then we can sort of invert that population and then say, okay, let's distribute all the binaries with that same population of magnetic fields. If we do that, we get basically up to about 25 per year of detectable neutron star events, giving you within the Fermi detection limit RSF, and about 5 per year for neutron star black holes. This wasn't a huge rate, but it may be the dominant one for neutron star black hole binaries. Again, this is with a really generous assumption. So these are upper bounds. What do these things look like? Well, if we saw one with 72817, so this is the Fermi data from 72817. 72817 was weird, right? It was off axis, so it was quite dim. If we saw an RSF, it would actually, with a strong field, it would have actually dwarfed the sort of off axis gamma ray burst that we did see. The only reason we saw this guy was because it was so close. Though there's something interesting here. We can put an upper bound on the magnetic field that we can get out of or that we can that these progenitors could have had in order for us not to be able to see a resonant shattering flare, and that ends up being about 10 to the 13.5 Gauss to sort of be below sort of 3 sigma. A more sort of normal case you might expect. So here's a short gamma ray burst, and then we just injected a So this is at 170 megaparsecs. And that's sort of a more normal looking precursor. And even with high fields, you still get not that big of a bump compared to the beamed emission. If you're a gamma ray observer, you might say, wait a second, these are relativistic blast waves moving through an interstellar medium. There's going to be afterglows, right? You plow through this material, it causes a shock, causes synchrotron emission, and you should get an afterglow at sort of all wavelengths. And indeed, we can do that calculation. If we stick in an RSF prompt emission that was basically just not detectable for 1717, we could then plot what the afterglow would look like. And you can actually have seen the afterglow in the X-rays and the optical if you had gotten on it fast enough. So within 1,000 seconds or so. I mean, good luck, but it's certainly physically possible that you could have seen the afterglows from this before the off-axis afterglow came over. I don't think we'll ever see, maybe in the radio, maybe with SKA for orphan flares. So for orphan flares, just ignore the SGRB part, right? The X-rays are going to be difficult, maybe with sort of faster slewing. The R band, I don't know. I doubt it. I doubt that will ever be able to be picked up unless people get super lucky. Radio, we may have a chance with once SKA comes online. Okay? So maybe you can pick up the afterglows from just these things. Okay, it's sort of comparable to, it's brighter, but still comparable to sort of kilonova afterglows, if you sort of looked into those. Okay. Oh yeah, this is my. We can bound the prompt emission so that our surface field we know is less than 10 to the 13.5 Gauss. Kelsoprees, right? That's a okay. So the last thing I wanted to get into was two really interesting, really cool detections that just came out. 211211. If you know anything about gamma ray bursts, then you probably have already heard about this. It is smack dab in the middle in terms of the hardness T90 duration plot. Smack dab in the middle of the population of what we call long gamma ray bursts. Long gamma ray bursts are thought to be how progenitors that are core collapse supernovae. And they're often accompanied by supernovae. They're in storm-forming regions. They're nothing to do with merging neutron stars. However, 211211 had a kilonova. So its sort of progenitors were what we normally call the progenitors of a short gamma ray burst, but it produced a long gamma ray burst. And if you sort of look at this emission, it does look a little bit weird. There's this sort of extended part of this emission. And that extended part of the emission probably comes from a magnetized remnant, probably from merger of two neutron stars, and then the remnant lasted long enough to be able to expel out magnetically a bunch of flux. And that is what gives you this sort of long-lived tail. So that sort of implies that this is sort of fairly magnetized object, at least one fairly magnetized object merging. Interestingly, there's that little blip there. There's a precursor. That precursor sits right there. You can zoom in, and you can. We know it's host galaxy, so you can look at it. It's relatively soft, and you can work out the estimates. And it sits right around where we'd expect a fairly bright RSF to be, and the surface implying that the surface field has to be greater than 10 to the 14.5 Gauss. Now, I'm not 100% convinced that this event was indeed an RSF. It has the characteristics of it, but the easiest person to fool is yourself. So I'm skeptical still. But then there was another of this really weird class that we've never seen before. It looks like a long GRB. Again, right in smack dab in the middle of that hardness ratio duration. But again, there was a kilonova. This implies that there's probably a population of long GRBs, which we never knew came from neutron star mergers. And now it's hard to separate out. There's basically doesn't look like there's a precursor here until you look at the soft versus hard emission. And turns out that if you do that, you get a fairly soft precursor. It's just not that well separated from the rest of the emission because of this little soft blip here. Indeed, if you put it on the same plot, so this is the peak energy versus the minimum variability time. Now, if you know about short gamma ray bursts, you know that it tends to be that with higher peak energies, with sort of harder bursts, you get faster variability time, right? Both these precursors, these are these dots here, have low E peak, so E peak around 200 keV, but still very fast variability time. So that could be a signature of what to expect. It basically implies that you have a slightly different mechanism, physical mechanism causing these precursors than the rest of the emission and the rest of sort of standard GRB emission. So that's sort of good news for this kind of model. I'm still not 100% convinced. There's no definitive proof. The definitive proof has to come from this multi-messenger comparison. Okay, so some conclusions. What do I want you to take away from this? For astrophysicists, I want you to take away that nuclear physicists want to understand many-body interactions of bulk nuclear matter. You can't, many-body QCD is too hard, so we write things down and then Taylor expand, right? And so getting those Taylor expansion terms is the job of very many experimental nuclear physicists. We can get at some of this stuff, particularly about the symmetry energy, by exploring the part of the neutron star where we know it's nucleonic, specifically not the core, but really the crest. RSFs, because of where they're located and because they can be induced resonantly, causing gamma ray flare, give us this early access to asteroseismology, which we really wouldn't expect to be able to do until the next generation of gravitational wave detectors. And with that, we can probe things like the symmetry energy to really decent precision compared to the the heavy ion colliders. Wait, I think I had more. Right. So RSFs can appear as precursors to SGRBs. We expect there to be orphans. They may be the most common black hole neutron star counterpart, but they require significant surface field, so you don't expect them for every single merger. Most neutron stars aren't that magnetic. So because they need to last a long time, core field is probably required. The way to turn this around is you say, if any of these are indeed RSFs, then you have to have this long-lived magnetic field population. At the very upper bound, you have 25 per year of binary neutron stars and 5 per year of black hole neutron stars. And I just want to, right, and then there's precursors for these two extended things. And I just wanted to end with advertisements. At Bath, we have a PhD studentship coming up. I'm trying to advertise one working on nuclear pastas and how it interacts with neutron star dynamics, particularly transport properties for nuclear pastas, which I'm still not quite sure how to calculate, but Will has some ideas. So we're at least trying to get some ideas. By transport properties here, I mostly mean like shear moduli. There are different UK research fellowships available. If you know of any good master's students in Spain, they're eligible for our international, the Bath University's international student fellowships, as well as if you know of any postdocs or graduating PhD students, there are plenty of UK research fellowships, which I would be very happy to support, particularly if you're interested in doing neutron star work. Additionally, I think we have a theory lectureship coming up. We just had an astro lectureship search. that just happened, but I believe there's another theory position coming up that's more general theory, so open to nuclear people as well. I'm leading with Sebastian Guillot, this effort called Compare, where this is as opposed to compose for instance. I just thought it was funny to call it Compare. It doesn't stand for anything. Where we want to provide the data, the posteriors, and the metadata for all sorts of neutron star observations so that modelers, and particularly the nuclear side, can use those data for comparing to their nuclear physics models or their astrophysical models. And sort of the next iteration of that, we'd also like to go the other way. We'd also like to pull from the nuclear side the experimental results, their posteriors, as well as the metadata that we need to use them. Really, the metadata is the important thing, right? Is because we're all in different fields. We don't know, like, the worst thing you can do is give a theorist data that they don't understand. They can make anything up, right? So that metadata is very important. So this is an effort we call Compare. We're just starting up. We've sort of entered a lot of the astrophysical data already, but we still need to build all the tools that we want to provide so that people can use this data reliably and easily. Sort of towards that, we are organizing a conference at the, we are organizing a workshop at the Lorentz Center called XMXS, Extreme Matter and Extreme Stars. The tentative date is the 23rd to 27th, next September. Here, the goal is for us to bring together nuclear physicists and astrophysicists and figure out how we talk more, how we exchange data, so on the astro side, how we provide measurements that can actually help in the nuclear physics. And for the nuclear physicists, how they can provide data that we can actually use for our astrophysical inferences. We are getting to the point now where we can actually start helping each other, but we need to talk the same language. So that's the goal of this workshop. We're still we're almost approved. We just need to respond to some referee comments. And then, so we have a tentative date in September. It's a bit annoying because it's during term time for a lot of people, but that's the best we could do. So anyways, that's all I had to say. Thank you.
Let's do a few quick questions if there is some left. I mean, I have loads as you might expect, but yeah. And then do you have one?
I don't know if there is two things I want to ask.
I did see one.
Okay, so I have just a couple of very
Yes,
fast,
yes.
and then afterwards we will read about it. So first one is, do you expect oscillations in the precursor? They are not detectable at the moment.
So I find it difficult to, so there was some hints of QPOs in those in 21, 12, 11, right?
Mhm.
They were like 3 cycles. And whenever you have a QPO that's 3 cycles long, I don't believe it. But I find it very difficult to imagine why. You have to remember that the photospheres of something like a resonant shattering flare or of any gamma ray source is going to be fairly far out, right? And you're not going to be able to see sort of surface oscillations necessarily. Now, there's a caveat there where maybe if you are shaking the field and you're sort of bringing into view, because these are fairly high gamma factors, right? So if you're bringing into view sort of slightly less magnetized versus slightly more magnetized, maybe you could do something like that. But it's a pretty contrived way of setting that up. So perhaps I think that you're working against a lot of physics, right? These photospheres are so far out. You really, it's difficult to connect it to physics sort of the neutron star sort of QPOing. Additionally, I never believe 3 cycle QPO claims. So.
Yes.
Probably less relevant question from nuclear theorists.
Oh, no, not at all.
So actually, I noticed somewhere you described the nuclear phase using the Skirby crystal, if I understand.
Yeah,
correctly. In that kind of studies, Do you also take into account like the spatial anisotropy, or you are consider isotropic space? Because I'm asking because some deformation can be done by the rotation of the star or the magnetic field.
Yeah. So we don't include sort of all our material properties are isotropic. That we put into our models, right? You would definitely have to worry about anisotropy in when we stick in pastas. This is part of the reason why we haven't done it yet. I should add, I actually think our frequencies are a little bit high currently because we haven't included this pasta region. We just assume that it's a relatively fast drop to zero. But it's probably an extended one where you have slightly less shear modulus there. In that case, you would expect the frequencies to drop a little bit. So this is something we're working on, but we don't have a good quantitative model of how the pasta region, say, has what the shear moduli are in the pasta region. So these things, so for the crust, we basically do everything through these extended skirm EDFs, plugging it through a liquid drop model. So it's probably relatively simple compared to things that you think about. But yeah, I'm always open to better interpretations of the nuclear physics because I just do what people tell me.
You are being modest.
All right, I think we'll probably stop here just in the interest of time, and people are probably hungry, but Dave is around for the whole day. He's in my office next to the kitchen upstairs, so you want to come and have another chat with him. So I suggest we thank Dave again. Thank you. All right.
Yep.
I think that it's the raining. Yes.